Okay, so before we begin, you're probably wondering, what is partial fraction decomposition? Well, it's pretty self-explanatory. The name kind of gives itself away. But essentially, what it is a way of integrating fractions. So, say for example, we have the fraction of x plus 5 over x squared plus x minus 2. Now, this is a totally solvable integral. However, without partial fraction decomposition, you would have to use a lot more calculus rules for integrating, and it would quickly become overcomplicated, and it would just turn into sheets upon sheets of paper, whereas instead we can use partial fraction decomposition, and just using a few different tricks that I will show you, it'll be quickly integratable. Okay, so before we get into showing you the methods of partial fraction decomposition, there is 3 key rules here that we have to remember when we are going to partially decompose fractions. So the first one is every polynomial can be factored into a product of linear factors and irreducible quadratic factors. So basically what this is saying is items such as this one here can be broken down into x minus 1 and x plus 2. And this will just make decomposing the fractions much easier if we just break down all quadratics into something similar to this. Now, the second thing is rational functions with a higher degree on bottom than on top can be decomposed into partial fractions. So basically is right here is so we can see that the degree of the denominator is higher than the degree of the numerator, so it can be partially decomposed. However, say, and this is where the third rule comes in, if the degree on top was higher than the degree on bottom, what we'd use is long division first. So say if instead of x plus 5 on top of x squared plus x minus 2, we had x cubed up top, then what we'd have to do is x squared plus x minus 2, and then we would divide x cubed plus 5, then we'd just go back and forth like this and use long division until we eventually factored out that degree and had a remainder. Okay, so back to our original example here to get started. So remember, the first thing that we want to do is we are going to want to break apart this factor, which we did earlier. So just x plus 5, we just want to simplify everything as much as we can. That should be a minus. So now that we have it in this format, what we can do is we're going to bring it over here, and we're just going to rewrite our equation. X plus 2 equals, and we're going to set up it in this exact manner. So this is going to be our first fraction, if you will. So we're going to call it fraction A. We're going to do A over x minus 1. And then we're going to add 1, and we're going to have fraction B. We're going to have B over x plus 2. Now, say theoretically that there was another factor that we broke out, say like another x or something, then we would have another c, and you would just keep doing this as you had more and more factors. Obviously, this isn't the case for this example, so we are going to ignore that for now. So next up, what we're going to do is we're going to multiply our denominator by this side over here. So what we will be left with is x plus 5 equals, right, because we're multiplying this over, is, so x minus 1 times x plus 2 times a over x minus 1. Obviously, these x minus 1s are going to cancel, so what we're going to have is a times x plus 2. And then over here, right, because we're multiplying by this entire side, we're going to have the opposite occur, where we're going to have plus b and we're going to have x plus 2 being divided by x plus 2, so we're just going to have b times x minus 1. Next, what we're going to do, now that we have our equation in this form, is we're going to choose a value for x that cancels out all but one of our terms. So what we want to do is choose a value that would multiply b times 0. For example, that way we can solve for a here. So obviously x minus 1, the solution to that is going to be 1. So we're just going to do 1 plus 5 equals a times 1 plus 2 plus b times 1 minus 1. So obviously, since this is going to 1 minus 1, this is going to 0, which multiplied by b is also going to 0. Now over here we have 6 equals a times 3. Now we can just bring over our 3 here, and we get 2 equals a. So now that we have this value, we're going to want to do the same thing, but instead for b. So for b, what we're going to do is we're going to have, obviously, x plus 2. The solution to this is going to be negative 2 to cancel out a. So we're going to have negative 2 plus 5 equals a times negative 2 plus 2 plus b times negative 2 minus 1. So over here we're going to have 3. A is obviously going to 0. And for b here, we're going to have b equals times negative 3, not b equals, sorry. So b here instead is going to equal negative 1. Now what we can do with these values is this equation up here. So let me clarify something. This is our original equation, so what we're going to do is we're going to take the integral of this. And that is the same as taking the integral of this one. Now, what about a and b here? Well, we just found these values, so what instead we're going to do is we're going to plug these in and take the integral of this instead. So we have 2 over x minus 1 minus, because of our negative 1 down here, minus 1 over x plus 2. Now, as you can see, this is a much easier set of fractions to integrate versus our original up here, because now this just turns into 2 natural log absolute of x minus 1 minus natural log of x plus 2. Now obviously, since our bounds aren't defined, we do still have a constant, and that will just be c. Now you can redefine your constant as something such as k. There are some people that do that. I personally find it confusing, and I just prefer to leave my constants at c. But say, for example, if we did have a third term over here plus c, right, you can see how that would get confusing. However, this is a personal choice, and I personally just like it better this way. So this is the answer to x plus 5 over x squared plus x minus 2. Now for our next example, we're going to be talking about another scenario, which I guess could technically be considered a fourth rule. But basically, what it states is for repeated linear factors, what we have to do is basically state the exponent multiple times as it goes on. So, say, for example here, we have x squared minus x plus 1 over x squared times x plus 1 cubed. So what we're going to have to do is we're going to set up our equation in the format that was shown in the last example. So we have a over x, right? Since this is already broken down. Alright, so what we're going to have here is a over x plus b over x, and this is where it gets tricky, is because we have x squared since we have 2. So when you have repeating factors, what you have to do is add the degree as you go along, almost like taking a factorial. So plus c x plus 1, right? This is just 1, plus d over x plus 1 squared. See, so as we move on to the next term, then we start having to add a higher and higher degree, plus e over x plus 1 cubed. So now what we're going to do is do the same thing. We're just going to multiply our denominator over here by this side of the equation, and I apologize, this is going to get a bit messy. So what we're going to have here is x squared minus x plus 1. Now, I forgot to note this, but the numerator, in most instances, we can just leave as is. We don't have to break it down into its individual factors, and that's mainly because we don't really have to deal with it until we're actually plugging numbers into it. Now, sometimes it can be useful to break it down, but you can always do that later, unlike the denominator, which you have to break down right away. So, back to what we were doing. So here, we're going to have a times x plus 1 cubed plus b times x plus 1 cubed, right? So the reason the x stays here is because we have an x squared and we're only dividing out by 1x. So we have a times x plus 1 cubed, right? Because none of those factors are being canceled out, plus c times x squared times x plus 1 squared, right? Because we only have 1x plus 1, but we have 3 over here, plus d times x squared times x plus 1 plus e times x squared. So now that we have our equation, so if we plug in a 0, then everything other than b will disappear. So we will have x squared minus x, or 0 squared minus 0 plus 1 will equal a, which will just go to 0, and then we have b here, and we'll have 0 plus 1 cubed. Then we have c, which will go to 0. Then we have d, which will go to 0, and e, which will go to 0. So we can begin solving. So 1 equals b. And then for a, this should all share relatively similar traits. So if we plug in -1, we should get all but e to cancel. So if we do this, we're going to have -1 squared minus -1 plus 1. Let's see, these two, well, 2 plus 1, that'll go to 3, because 1 plus 1 plus 1, 3 equals, and then a, if we throw in -1, -1 plus 1 goes to 0, Negative 1 plus 1 goes to 0. Negative 1 plus 1 goes to 0. Negative 1 plus 1 goes to 0. And then that'll just leave us with e. So 3 equals e. And then from here we can just start slowly picking away until we get the rest of our values, which I will do right now off screen just to save time. So after finding A, C, and D, we can plug our values back into our equation up here and begin to integrate. So we have the integral of negative 4 over x plus the integral of 1 over x squared plus the integral of 4 over x plus 1 plus the integral of 3 over x plus 1 squared. And finally, we have the integral of 3 over x plus 1 cubed. Now, what we can do just to make our lives easier is do the standard integration technique where we pull out our constants. So negative 4, this is just going to 1. We're just going to pull this all outside. This goes to 1. This goes to 1. Oh, oops, getting backwards here. And this goes to 1. Now this will make this much easier to solve, because now instead what we have here is essentially a bunch of log functions, with the exception of the x plus 1s. So we have minus 4 natural log x, then we have minus 1 over x, then we have plus 4 natural log of x plus 1, then over here we have minus 3 over x plus 1, and finally we have minus 3 times 1 over 2 times x plus 1 squared. Now we can't forget our constant of integration c, and that is this integral up here solved.